Here we go with another one of the gas laws. So this is Charles's law. And here we're going to talk about we're going to talk about this as if this is a magical syringe, okay? Where the syringe can move up and down so that the pressure outside, so the pressure out here, is equal to the pressure inside, okay, in here. So this is just a fancy way of saying that if something would change the pressure, rather than changing the pressure, it's going to change the volume to counteract that effect. Okay? So the question here is, what happens if you increase the temperature inside of the gas, inside the syringe, when you have this condition where P outside equals P inside? Okay? Well, what happened before? The particles inside, okay, are going to start moving faster. Okay, so particles move faster. Now, normally we would say that would create more collisions, which would increase the pressure. Okay? However, something to keep in mind is pressure must be held constant. So we know that there are more collisions, which would usually increase the pressure. But if the pressure is going to be constant, the way that the system shifts is to increase the volume. Okay? So that, remember that if volume increases, pressure decreases. Okay? So we can say that if the temperature increases, the volume would also increase, which means that volume is directly proportional to temperature. Okay? So why don't you pause here and get the last law? You should be able to do it at this point, okay? And then when you come back, I'll solve it out for you. So pause here, do it. So again, in order to go from a proportionality to an equality, we just have to add a constant, V equals KT. Now notice that this constant is different from all the other constants. It's a different constant every time. Every time there's a system, there's a different constant. Okay? So I can turn this eventually into V1 over T1 equals V2 over T2, okay, by dividing both sides by T here and saying V over T equals K, and K must be constant, so V1 over T1 equals K equals V2 over T2, and then solving for getting rid of the K, sorry. So another thing to keep in mind here, this temperature, again, has to be in Kelvin, and that's super important. All right? So now that you know the theory for Charles's law, and by the way, V1 over T1 equals V2 over T2, this is Charles's law. Let's see a problem. Balloon filled with oxygen. Okay? So actually, first step is going to move this down a little bit so I have some breathing room. All right. Balloon filled with oxygen occupies a volume of 5.5 liters at 0 degrees Celsius. What volume? There's my volume again. Oops. Okay. Here's my 0 degrees Celsius, and here's 100 degrees Celsius. A balloon filled with oxygen gas occupies a volume of 5.5 liters at 0 degrees Celsius. What volume will the gas occupy at 100 degrees Celsius? So this is going to be V1. This is going to be T1. Notice that we're going to have to change this to Kelvin, so that's 273.15 Kelvin. This is V2. And then this is T2. And why don't you quickly convert that to Kelvin? So that's 373.15 Kelvin. All right, so now we're ready to start. I'm talking about the relationship between volume and temperature. So that's Charles's law. V1 over T1 equals V2 over T2. Okay. I'm trying to isolate V2. That's what I'm trying to isolate. So I'm going to multiply both sides by T2 over 1. So V2 equals V1 T2 over T1. So that equals 5.5 liters times 373.15 Kelvin, T2 up here, divided by 273.15 Kelvin. Okay, equals 7.5 liters. All right, I have two significant figures from here. This should probably be 0.0 degrees Celsius just to keep everything honest with sig figs. And that's it. Okay, so why don't you try the next problem and see how you do.